Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the final video in a series on the fundamental theorem of calculus. You should have already watched and probably done some problems using the fundamental theorem of calculus parts 1 and 2 prior to starting this video. Mainly because I assume at this point you're not like incredibly proficient with it, but you can actually use those theorems. So let's now go into the higher level material. And again, this is not going to venture too far away from the fundamental theorem of calculus parts 1 and 2. It's just kind of pulling together older concepts and using them in this new framework. For example, find the x value for the local maximum of the function f. Well, before you even gawk at that terrible looking function, just remind yourself, how would you find a local maximum for a function? I mean, think back to what you did. If somebody said, I swear I know how to find a local maximum. Well, these are maximum. This is a maximum right there. How would you find that local maximum? Well, there's one way to find that specific one. Take the derivative and set it equal to 0. Find out when the derivative of your function is 0. But local maximums also can occur at kinks, right? Or cusps or corners, whatever you want to call them. And that occurs when your derivative does not exist. So we want to look where f prime does not exist or f prime is 0. So we basically want the critical numbers of f. So let's go ahead and take the derivative with respect to x of f, which is the derivative with respect to x of the integral from 0 to x, t squared minus 36 over 1 plus the cosine squared of t and dt. Don't forget about that dt. And let's go ahead and take this derivative. And I do want to mention here that when I built this, maybe I should have built this and called this 11, mainly because I don't want that denominator to ever become 0. So let's just call that 11 down there, mainly because I don't want to have domain issues. Okay, and oh, actually you won't have domain issues. Ignore what I just said. All right, so by the fundamental theorem of calculus part 1, this will equal x squared minus 36 over 1 plus the cosine squared of x. And again, that's by the fundamental theorem of calculus part 1. So that's the derivative of our function. And we're asking ourselves, when does that not exist? Well, its denominator is 1 plus something that's at least 0. So denominator will never be 0. So this function or this derivative always exists. Then we need to ask, when is the derivative 0? Well, f prime is equal to 0 when x is equal to plus or minus 6. Okay, perfect. That is awesome. Draw out a number line and then test values. When you, let's just pick something in this middle region. When you plug in 0 to f prime, you'll get a negative. So our function was decreasing on that interval. When you plug in any number less than, or actually greater than 6 or less than negative 6, it's the same situation because you're squaring it. So that'll be, let's see, something greater than 36 minus 36, that's positive. Denominator is always positive. So in both cases, these are positive and your function is increasing on both of those intervals. And the question was, find the value, x value, for the local max. Local maximums occur when a function goes from increasing to decreasing. So there must be a local max for our original function. So our original function being this integral. So f, which is the integral from 0 to x of t squared minus 36 over 1 plus cosine squared of t dt has a local max at x equals -6. Now you may look at that and go, wait a second, but that's counting backwards, because if I plug a -6 in for x, I'm going from 0 to -6. That's the wrong direction. That's still okay. We can totally do that. You can always flip the signs of integration. If we went from 0 to -6, that's the same thing as going from -6 to 0. So you just flip the limits of integration, and it forces a negative in that integral. So we're totally okay. Anyhow, all right. So that is the answer to that. Very nice question. It pulls together topics from optimization, which is a major topic prior to integration. Let's do something old school. Find the equation of the tangent line for some function, right? So finding an equation of a tangent line for this function at x equals 2 is interesting, to say the least. So what do you need to find the equation of a tangent line? Forget the fact that it's an integral here. Just think about what creates a line. Well, you need a slope and you need a point. Well, they give us that x equals 2. We want to find the equation of tangent line at x equals 2. So the point is going to be 2 comma something. Well, 2 comma f of 2, honestly. Right? Because that's the function value at 2 is f of 2. Well, let's see what f of 2 is. F of 2 is the integral from 2 to 2 of I don't care, because the integral from 2 to 2 is 0. So this is going to be 2 comma 0. So we have our point. Now I need a slope. And to find a slope, I need the derivative. So let's take the derivative of that function. F prime of x is equal to derivative with respect to x of the integral from 2 to x of the cosecant of the square root of t squared plus 8 and the cosecant dt. But we know the derivative of the integral is just going to be the cosecant evaluated at the upper limit. Normally I'd say times the derivative of that upper limit, but we know the derivative of that upper limit is 1. And I also would say minus the cosecant evaluated at the lower limit, but then when you multiply that by the derivative of this lower limit, that would be 0. So I don't need to worry about that. And by the way, this is by the fundamental theorem of calculus part 1. So that's our derivative function. Okay. What do we want to do with that? Well, I need the slope at time 2. So I want to know what f prime is when I plug in x equals 2. Well, that'll be the cosecant of the square root of 12, which is really, I don't know what that number is, right? So cosecant of the square root of 12 is what that is. So let's go ahead. It's a number. That's all that matters. So our slope is the cosecant of root 12. Let's go ahead and write the equation of the tangent line. The tangent line has this equation: y minus the y value of the point is equal to the slope, which is cosecant of the square root of 12, it's just some number, times x minus the x value of our point. So this is our equation of our tangent line at x equals 2 for that integral function right there. So it really is. You could pull together a lot of the stuff you've done throughout your calculus course and do things with integrals now. Now this question is near and dear to my heart. And the reason why I say that is because I love to preview Calc 2 when I'm teaching in person. I think Calc 2 is such a beautiful topic that previewing it to a class when you're in front of them is when they're first learning calc integration is really astounding. People honestly, people really dig it. It's just one of those things that it's hard to explain. Anyhow, this kind of knocks on that door. Consider the region bounded by the y-axis, the line y equals 1. So I'll just go ahead and draw the line y equals 1 in here. We'll just say that's it, y equals 1. And the curve y equals the fourth root of x. Well, the curve y equals fourth root of x looks something like this. Okay. It actually continues on, but I'm just going to keep it like that. Okay. All right. So consider the region bounded by, again, the y-axis, that blue line, and that green curve. Very common question from a Calc 2 course, saying you have a region, here it is right here. That is super common to have to graph out. And that's why, again, having strong algebra skills is critical in Calc 2, because you need to quickly graph out stuff like this. Find the area of this region. Now that should cause you to pause for a moment, because we have so far found areas under curves to the x-axis, right? But we haven't found areas under curves to the y-axis. But you totally can do it. Tilt your head to the right. And imagine I put boxes this way instead. And you can probably guess that I'm building a Riemann sum. Although I don't need to, because I'm not going to use Riemann sum here, because now that we know how to integrate a definite integral using the antiderivatives, we don't need to use Riemann sums for the time being. You'll need them later on, but for now we don't have to. So let's find the area of this region by, instead of looking at it the way they've drawn it, by tilting our heads and integrating with respect to y. To integrate with respect to y just means you have to look at the world slightly differently. That area is going to be the integral starting at y equals 0 and ending at y equals 1. We're stacking boxes from y equals 0 to y equals 1. I hope that makes sense. And we need a function here, and then we're going to say we're taking that integral with respect to y, because each of these widths are little delta y's. That's a terrible delta. Let me rewrite that delta. There we go. I have rewritten that delta. Each of those little widths are delta y's, which when you throw them into an integral are dy's. But we still need a function. What is the function that we're integrating? Well, if you take a look, the function we're integrating is this guy right here. Now, it would be very illegal if I were to say, hey, let's integrate from y equals 0 to y equals 1, the fourth root of x. Let me write that in red. dy. That is illegal, because you're integrating with respect to y something that is not y. You need to rewrite that function in terms of y. But luckily, I can, because we know that y is equal to the fourth root of x. That is, we know x is equal to y to the fourth. And that is our function. We're going to integrate not the fourth root of x, but y to the fourth. That's our actual function we're integrating. There you go. Now ask yourself, what would you take the derivative of, if you're taking derivatives with respect to y, what would you take the derivative of to arrive at y to the fourth? If you said y to the fifth over 5, you are absolutely correct. I'm going to write it as 1/5 y to the fifth, but it is y to the fifth over 5. And you're going to evaluate that from y equals 0 to y equals 1. Plugging in that upper limit, you get 1/5 times 1, minus plugging in that lower limit, you get 1/5 times 0. That's why zeros are great as limits. So this answer is 1/5. That is the area of that shaded region. Being able to turn your head and look at the world slightly differently is so important, not only in mathematics, just in life. Turn your head every once in a while and look at somebody else's perspective. You might learn something. Stepping off my soapbox, let's ask, this is a very common style of question that I put on exams. Let's ask, what's wrong with a computation? So a student comes in and they say, okay, I have this definite integral of secant squared. Well, I happen to know that the antiderivative of secant squared is the tangent. So that looks right. And I'll evaluate that from 0 to pi. The tangent of pi, well, that's 0, minus the tangent of 0, well, that's 0. So I don't see anything wrong. If you say you don't see, there's nothing wrong with this, then you got to know. Your instructor's not going to say what's wrong with this computation if there's nothing wrong with it. There's something wrong with this computation. Stare at this. Pause this video until you figure it out. Are you back? Because I'll tell you right now what the issue is. We have a secant function. Secant functions look like this. Well, they're not that nice, but whatever. But they have vertical asymptotes. And the vertical asymptote on the interval that is in question occurs at pi over 2. Let me read there. At pi over 2, this function has a vertical asymptote. So the problem is that secant, it's not defined halfway through that interval. So this is not continuous on 0 to pi. It has a discontinuity at pi over 2, so you can't integrate it. And that's a problem. And if you ask, well, can I break that into the integral from 0 to pi over 2 and then the integral from pi over 2 to pi? I would say no, because again, your secant is not defined at that edge. So you can't even do that. This is broken. Now, there are techniques that you'll learn pretty much at the midway point of Calc 2 where you can deal with this. But right now, we would just say we can't do that. And you shouldn't be handed a problem with this type of discontinuity in it, unless it's a question like this, like what's wrong with this? Now, this question is often reserved for the future section, a section we get into in a little bit, but I find that it doesn't really fit very well there, so I like to do it in this lecture. The velocity function, how fast something's moving in meters per second, for a particle moving along a line is given by this. V of t is equal to t squared minus 2t minus 3, where time is going from 2 to 4 seconds. Find the displacement and the distance traveled by the particle during the given time interval. So you might say to yourself, or you might ask yourself, what's the difference between displacement and distance traveled by the particle? And those are very strong. There's a very strong difference between those. The displacement is ending position minus beginning position. I went ahead and wrote that in there. But the distance traveled, that's completely different. Imagine you start at your house, home, and you go to work. Well, the displacement might be, let's say, for me, actually, when I live about 50 miles away from where I work. So that displacement is 50 miles for me when I go from home to work. Okay. And that's why it upsets me when I have somebody who misses an exam and says, hey, can you come in on your day off to give me an exam? I say no, because I don't want to drive a 100-mile round trip just to give you an exam. Anyway. Okay. So my displacement, if I go from home to work, 50 miles. If you go from home to work and then back home at the end of the day, the displacement is 0. You've actually technically had no net movement, right? You went 50 and then minus 50, but the distance you traveled is 100 miles. That's the difference. Displacement, if I start at home and end at home, my displacement is 0. But really, the distance is what happens in between, what really did happen. You drove 50 and you drove 50, that's 100 miles. So kind of distance is what your odometer has, right? And displacement is your position difference between the beginning and end. And I wrote that as the total of all absolute value movement because mathematically, when you compute distance, you'll be using absolute values. Let me go ahead and erase this piece and we'll tackle this problem and showcase the differences here. First of all, when you have a velocity function and you want to find a total distance traveled, think geometrically here. They give me a velocity function in terms of time. Velocity is given in meters per second. Time is in seconds. So the area underneath the curve should have the units meters per second times seconds, or in other words, total meters traveled. So if I want to find a displacement or a distance, really I want to integrate that function v of t. That will give me a distance in meters. So let's go ahead and set up an integral. The integral from 2 to 4 of v of t dt, or in other words, the integral from 2 to 4 of t squared minus 2t minus 3 dt. By the way, some people get asked the question when I teach in class, why do I sometimes put parentheses around these statements and why do sometimes I don't? Well, it's just a personal moment of spur of the moment decision. Sometimes I do, sometimes I don't. Generally speaking, if you start with an integral sign and end with a differential, the stuff in between is the integrand. So you technically don't need a parenthesis. But if I have a very large integrand, I like to write parentheses every once in a while. So let's take a look at that integral. Let's ask ourselves, what is that? Is that the displacement or is that the total distance? Well, that right there is going to be displacement because if you remember by the fundamental theorem of calculus part 2, this is going to be the position. Remember, velocity is what we're integrating, so it integrates to become the position. It's going to be position at time 4 minus position at time 2. In other words, ending position minus starting position. So this is going to be the displacement. In other words, where if we've moved back and forth throughout the day, but in the end, we only end 1 foot away from where we started, our displacement would be 1 foot, even though we may have walked 3,000 feet during the day. Okay. So here we go. What are the antiderivatives here? Well, the antiderivative t squared is t cubed over 3 minus the antiderivative of 2t is actually t squared. You could double check by taking its derivative. Each of these, by the way, you should always double check. Take the derivative of that. The derivative of t cubed over 3 is 3t squared over 3, which is t squared. The derivative of t squared is 2t. Well, specifically negative t squared would be a negative 2t. And then finally, the antiderivative of negative 3 is a negative 3t. Double check. The derivative of negative 3t is totally a negative 3. And you're going to evaluate this from t equals 2 to t equals 4. This is probably the arithmetic version of the worst case scenario because you're just going to have to do a lot of arithmetic here. We'll plug in the upper limit. So I get 64 thirds minus 16 minus 12 minus, and then we'll plug in the lower limit. That's 8 thirds minus 4 minus 6. Notice the parentheses that I use after the minus sign here. You have to do that, otherwise you'll make sign mistakes. 64 thirds minus 8 thirds is 56 over 3. Negative 16 minus 12 is a negative 28. Let's see, and this is a negative 10, but you have a minus in front of it, so it's a positive 10. And what do we get? 56 thirds minus 18. And that 18 is the same as 18, 30, 54. Yeah. So 2/3. So the net change in distance, the net displacement is 2/3 of a meter. So displacement for this particle is 2/3 of a meter. Equals 2/3 meters. Not a lot, right? Now, if you want to add up all of the distances and get the actual distance traveled, think of it this way. You have this velocity curve. Right? Now, if the velocity is always positive, then you're absolutely adding positive, 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 positive. And so the displacement would be from time 0 to time, or in this case, from time 2 to time 4, would be an ever increasing displacement, so it'd be much greater than 2/3. Okay, but really what's happening in this situation is that we have a positive velocity at some point and a negative velocity, and then it goes positive again. And so you have some positive area here, that's a positive distance traveled, and then you subtract off this area, that's subtracting off some distance, and you're adding back some distance in the end. And so the net result of that would be our 2/3 meter movement. But what we really want to do is take the absolute value of that. So the absolute value would take that curve and flip it upside down. Well, I wouldn't flip it upside down, but it'd flip it. So let's take a look at this. How will we do this? I'm going to graph the velocity function t squared minus 2t minus 3. So let's graph. Now you have your own ways of graphing parabolas, and I have my own way of graphing a parabola. So we will differ, and we'll be okay with that. So at time 0, I know the parabola is at that height. It's at that height again at time 2, and it opens upward. So the parabola looks something like, and at time 1, 1 minus 5 is negative 4. So it looks like this. So here's what the parabola looks like. Okay. This is time 2 right here. And this, when it's time 0, it must be time 3. Is that what it is? Yeah, 3. And then time 4 here. Okay. So notice we do have a negative area and a positive area, right? So what we need to do is we need to take that negative area and flip it. And so we are going to take the integral from 2 to 4 of the absolute value of v of t. That's how you compute distances, not displacement, but distances. And when you compute that, what it's going to do to this curve is it's going to flip the part that was down there that did this. It's going to flip it. Yeah, this way. Make it look like that. Okay. So we'll have a positive distance and more positive distances. And that's what you want to do. You want to force all of your movements to be positive movements in terms of mathematics. So let's go ahead and do this here. We know that between time 2 and time 3, our velocity is actually negative. Remember, when I graphed it, the velocity graph was negative between time 2 and time 3. So I need to, what the absolute value is going to do is, if we recall from the beginning of your calculus course, the absolute value of something is equal to, well, if that something was already positive, you could just remove the absolute values, right? So that's true if the whatever you were taking the absolute value of was already positive. But if whatever you're taking the absolute value of was negative, the absolute value will return the opposite of it. It'll force it to be positive by putting an opposite sign in front of it. And again, that's if whatever you were taking the absolute value of was negative. Okay. So between 2 and 3, our velocity function is negative. So we're going to take the opposite of our velocity function to force it to be positive. And then between 3 and 4, our velocity function was positive, so there's no need to have an absolute value. That's how you compute a distance. You break it into pieces. The pieces where your function is negative, you're going to take the opposite of the function. The pieces where your function is positive, you're going to keep your function as positive. Let's go ahead and evaluate this integral. We have the negative integral from 2 to 3 of our function v of t, which is t squared minus 2t minus 3 dt, plus the integral from 3 to 4 of v of t, which is again t squared minus 2t plus 3. These look very similar mechanically, but actually mathematically they turn out to be somewhat different, although the antiderivatives are the same. So this is going to be negative, and then we'll have the antiderivative here, which we already knew was t cubed over 3 minus t squared minus 3t. We're evaluating that from time 2 to time 3. And again, I'm showing you different forms of how people write this. Some people will write t equals 2 to t equals 3. But as I've just done, I'm writing just t from time 2 to time 3. The next integral, oops, I didn't mean to go to a different ink there. The next integral, again, same antiderivative, t cubed over 3 minus t squared plus, oh, is it plus or is it minus? I didn't mean to write plus. That was supposed to be a minus. Minus 3t, evaluated from 3 to 4. All right, let's go ahead and plug these values in. I'm going to keep this negative on the outside of this because it gets confusing if you start trying to move things around. So I'm keeping that negative on the outside. Plug in a 3, you'll get 27 over 3 minus 9 minus 9. And we're going to subtract off plugging in 2. So that's 8 over 3 minus 4 minus 6. Close off all those parentheses. Move over to the next one. We have plus. Plug in a 4. You get 64 thirds minus 16 minus 12. And then minus, plugging in the lower limit, we get 3 cubed over 3. That's 27 over 3. Minus 9 minus 9. You would think things cancel between plugging in lower limits and upper limits that are the same, but they don't necessarily. Cleaning this up. I'll keep that negative on the outside while I clean this up. 27 thirds is the same thing as 9 minus 9, so those cancel out beautifully. I have a negative 9. Let's see, losing a negative 10 is adding 10, so we have 1 minus 8 thirds here. Plus 3 does not go into 64. So I'll leave that 64 thirds there for the moment. This is minus 18. And this is 9 minus 9, that's gone. Plus 9, 18. Negative 18 plus 9 is negative 9, actually. And now combining things up, right? So I have a positive 8 thirds and another 64 of them. So I have 72 thirds. Just make sure my math is right. Yep. I have a negative 1, losing another 9, so minus 10. 3 goes into 72 24 times. That's 14. Am I right with that? 360, yes, okay. My brain, right? So 14. So the total distance traveled actually by the particle was 14 meters, even though the true displacement was 2/3 of a meter. So that's sort of like saying something wiggled back and forth, and where it ends was only 2/3 of a meter away from where it started, but in reality, it traveled 14 meters during that entire time. So that's a good, robust problem. Continuing along the same vein, this is, again, one of my favorite problems. It's the absolute 5 times the absolute value of sine of x from 0 to 3 pi over 2. That absolute value, you should take that very seriously, graph out the sine curve, and find out where it goes negative. You know it's positive from 0 to pi, but it goes from negative from pi to 3 pi over 2, at least for the interval in question. So I could break this apart into the integral from 0 to pi, and on that interval from 0 to pi, our sine curve is above the x-axis, so there's no need for me to have absolute values there. Plus the integral from pi to 3 pi over 2, and on that interval, our sign is negative, and so the absolute value can be ripped away but traded for a minus, right? So this will be a minus 5 sine of x dx. Again, absolute values will return, you can just remove them if the function's already positive, but if the function is negative, which it is between pi and 3 pi over 2, you're going to replace that sign with a negative sign so that it forces positivity. And that's why we have that negative 5 sign. Let's go ahead and find antiderivatives. I'm going to move that 5 out. And the antiderivative of sine, what would you take the derivative of to get a positive sign? Negative cosine. That throws people off all of the time. Let's see, I'm going to factor off that negative 5 out of this one and ask the same question. What would you take the derivative of to get that positive sign? Again, negative cosine. And this you're evaluating from pi to 3 pi over 2. So those negative cosine antiderivatives are, I mean, I can catch students all the time on those, so be very careful. Let's see. I think I'm going to do one other thing before I start this. I'm going to factor the negatives out of both of these because they can get very confusing if you leave them in there. So I'm going to say that's negative 5 times the cosine of x evaluated from 0 to pi. And it's a positive 5 times, again, the cosine of x evaluated from pi to 3 pi over 2. Everything that I do is from well over a decade of experience teaching and seeing mistakes. So factoring the negatives off before you evaluate your antiderivatives is just so important. If you don't do that, it can lead to a lot of arithmetic mistakes. So let's evaluate that cosine at the upper limit and then subtract off the cosine at the lower limit. And the same thing in the next one, right? Cosine at the upper limit minus the cosine at the lower limit. And do not leave your answers like this. Those are simple trig functions. The cosine of pi is -1. Minus the cosine of 0 is 1 plus 5. Cosine of 3 pi over 2 is 0. Minus the cosine of pi is a -1. And now you have -5 times a -2 or 10 plus 5 times 1. And that's 15. That is the area underneath that curve 5 times the absolute value of sine of x between 0 and 3 pi over 2. You can see that there's a lot of little techniques that get involved, but the calculus isn't actually the hard part. It's all the little algebraic manipulations and remembering how absolute values work. And that will wrap it up for this video and all of the fundamental theorem of calculus topics. So from this point forward, you're just going to be integrating nonstop.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.